Hello, my name is Shingo Okuno. I'm an industrial researcher working at Fujitsu. Today, I'd like to talk about the relationship between Straggler-Tolerance and accuracy awareness in distributed training. As you know, deep learning applications are now widely used in various fields. The recent deep neural network models require a huge amount of computational power. So, distributed training on multiple workers is one promising way to shorten training time. One of the challenges in distributed training is to alleviate the impact caused by stragglers, which run training tasks abnormally more slowly than other workers. For example, in synchronous distributed training, each worker repeatedly executes each epoch in the order of computation, communication, and update like this. In this example, worker 3 becomes a straggler due to slowdown and causes synchronization delays, which lead to an increase in training time. We can avoid the performance impact from stragglers by straggler mitigation, which excludes stragglers from training. However, we face another problem of decreasing accuracy during training because gradients computed by excluded stragglers are not reflected in the model update. In multi-tenant cloud environments, we encounter stragglers with high probability due to the contention of shared resources. So this dilemma becomes more serious. But stragglers may recover from slowdown over time, or we can alleviate slowdown by live migration and etc. So as a solution to the dilemma, we aggressively exclude stragglers from training in anticipation of recovery from slowdown. And once excluded stragglers recover from their slowdown, we return them to the training. Such a solution can be implemented by auto scaling, which means training job is scaled in for worker exclusion, and training job is scaled out for worker reinstatement. Also, there are some distributed training implementations supporting auto scaling. They have evaluated only training throughput. So we investigated how straggler mitigation and excluded straggler reinstatement affect accuracy during distributed training. Now, I'll explain the excluded straggler reinstatement using this example. We use aggregated training throughput to determine which workers are excluded or reinstated. We assume worker 3 are excluded from training because the throughput without worker 3 is greater than that visit. After the exclusion, worker 3 continues computation independently of other workers, and it returns to training if the throughput can increase with its restatement. When worker 3 satisfies the requirement, it sends a notification indicating its restatement to other workers. Then it jumps to the epoch where other workers are in training, and it updates its model state by inter-process communication from other workers. After the restatement, all the workers continue training synchronously. We conducted the performance evaluations to examine the effect of the straggler mitigation and the excluded straggler reinstatement on accuracy during training. We trained the ResNet 50 model on ImageNet using 32 GPUs. We implemented our reinstatement mechanism by the PyTorch distributed package. To simulate an occurrence of stragglers, we set part of 32 workers to call an artificial half-second sleep during a specific period. We assign training data among workers using the stick-to-shared option of the NVIDIA data loading library. When the option is disabled, each worker reads a different block of the dataset compared with the previous one in a cyclic manner. In contrast, when the option is enabled, each worker reads the same block of the dataset in all the epochs, and the dataset is not rotated among workers. By the stick-to-shared option, we can investigate the influence of training data assignment. So this page shows the top-down accuracy transition for each of the execution. The gray chart are the baselines where no stragglers occurred, and the others are the result with stragglers. In both the results, the stragglers occurred in the third epoch, and they are excluded at the end of the same epoch. We can see excluding stragglers decreases the accuracy. However, the accuracy degradation was minimized after the reinstatement. We observed the accuracy difference of 10% or more between the result with or without the reinstatement. We also found the two interesting findings from the result. First, there was only a tiny difference in the final accuracy. This might be caused by the model or the dataset we used in the experiments. So we will conduct experiments using other models and other datasets. Second, the training accuracy greatly decreased immediately after the reinstatement. This is because the model was optimized for the dataset used by the workers participating in training. We need to alleviate this degradation to improve accuracy further in training. To evaluate the accuracy during training quantitatively, we calculated the total sum of the accuracy difference from the baseline in each epoch. The bar chart are the result with the reinstatement, and the line ones are the result without the reinstatement. The horizontal axis denotes the length of the exclusion period, increasing from left to right. We can see the accuracy degradation was alleviated as the number of excluded stragglers decreased and as the exclusion period shortened. We also found the reinstatement was more effective in minimizing the accuracy degradation when stick-to-shared was enabled. This result indicates it is important to consider how training data is assigned among workers. So this is the conclusion of my presentation. Excluding stragglers is one of the important techniques in distributed training to obtain the maximum performance improvement. However, it causes accuracy degradation. We conducted the experiments and confirmed we can minimize the accuracy degradation by reinstating recovered stragglers into training. The reinstatement mechanism will be useful in these situations where the accuracy during training has a significant impact. In future work, we will further improve accuracy during training and will conduct experiments using other models and other datasets. So that's it. Thank you for watching my presentation.